Alrighty, so this isn't a lecture video. This is more so a problem walkthrough type video, a physics problem walkthrough video. In this case, we're going to go through here. Again, you know, Intro to E&M by Griffiths. We're going to look at this kind of first problem here. This is problem 2.1. Yeah, we're going to use some of the principles we learned in the lecture to work this thing out. Let me switch to mirroring here, my iPad. Recording, audio is good. Yep. Okay. Let's do it. Okay. So, you know, if this is sort of classic with physics problems, you know, the theory seems all right, you know, fairly straightforward, and then you get to the type of problems they ask you, and you're just like, what am I gonna do with this? So many words. Just here, he wants you to look at this sort of 12-sided polygon. You know, I don't even know how to like draw this. Is basically like a pizza. 12-sided, I mean, you know, and put a charge on each kind of corner and then analyze. There's these charges here are going to be like static. They're going to be fixed, like you build them and they're fixed. And then this is the thing here that's allowed to move in any kind of direction. We're not going to do that. We're not going to do that. The thing they don't tell you in physics is that the role of the physicist, figure out a more efficient way of carrying out or sort of delivering I'm literally just in a hallway, guys. I mean, you know, yeah, so there's going to be people walking in and out sometimes. Anyhow, the thing the physicist does is make this type of thing, like how can he get the same type of concept carried out in a more simplistic manner? Because we're human. And we don't have too much time. Sort of gloss over these like complicated geometries. We can do something a bit more simple, and you can still get the notion of what you're trying to look for in a problem. So let's do that. Instead of a 12-sided polygon, let's do a 4-sided polygon. Say a square. Okay. Suppose the sides of this square are exactly the same, even though I might have not made them exactly the same. Imagine them to be exactly the same. And you know, if you want, you can bring out a ruler and make them exactly the same. Sort of read the problem a little bit. They're equal charges. Okay, so that's something that we do have to carry over. And you know, yeah, they're at the corners of the polygon. Okay, so I think we got that set up here. We have Q1, positive. Q2, which is positive. No. Let me not do that. Let's put just Q2 over here, just because I like this kind of logic better. Q3, Q4. And, you know, somewhere exactly along the center of this square, there's a charge that we allow to move. It can be moving, right? Doesn't have to move, but it can be moving. These charges here don't move. They're static. You know, they were built right in there. They're not allowed to move. Okay, we're analyzing charge, the charge in the middle, so we call it big Q. Okay, and the idea with this problem is that, you know, this kind of polygon here, these are the distances that matter. Okay, so let me call this one R1, R2, R3, R4. Okay, because this is a square, the geometry, it works out that all these sort of R1s, R2, R3, and R4, whatever D is, everything will scale accordingly. These R's, whatever they end up being, okay, because these sides are equal, those R's will also be equal. Okay, so you have your charge in the middle and you have your charges outside. That charge in the middle is going to be in equilibrium. Okay, think about this. It's going to be pushed in every single direction equally. Let me show you. So, you know, I'm thinking, let me just copy this exact setup. Copy, paste it over here. Come on. There you go. Just kind of delete some stuff. Okay. You're going to have a vector that goes like this, all right? This is a force vector. This is due to those two charges. They're both positive, okay? Sort of right over here somewhere that, you know, Q is equal to Q1 is equal to Q2 equal to Q3 is equal to Q4. And, you know, say they're all positive, okay? They can either be all positive or all negative. You'll still get the repulsive interaction between them, which is that this charge doesn't want to be there. It wants to go away from the equally charged Q3. Okay. What am I doing? All right, so Okay, so this is, let's call this FO3, because it's the interaction with Q and Q3. We're going to have another force, okay, due to Q and Q4. We're going to have another force due to Q and Q2. Call this FO2. And we have another force due to QO and Q1. All right. All the charges are exactly the same. They're all going to be exerting equal amounts of forces on each other, meaning that this vector is going to cancel out this one. This vector is going to cancel out that one. And so you're going to end up with a particle like Q in the middle is not going to move anywhere. That is, if it's precisely at the center. The moment this thing is no longer precisely at the center, it's going to move away towards infinity because it wants to get away as possible from these guys. Okay. But if you get that charge to be exactly at the center, then it will be held in equilibrium, and you call that a unstable potential. Not a stable potential. Stable potential would be that this charge is, the moment it's nicked out of that center, it's just going to go off to infinity, and infinity is the stability. At infinity, far as possible from these guys. But we find that Q is in this kind of unstable potential well. And Q is at equilibrium right at that center. So this brings up the idea of, you're adding up these forces, F net, okay, which is going to be equal to F, okay, so FO1 plus FO2. You're just adding all these guys. You're adding them all up, okay, plus FO3 plus FO4, okay? Don't think too much about the numbers. Think about the fact that all these vectors, okay, are in opposite directions from each other, and eventually, in our case, okay, this isn't for all cases. In this case, where they're all canceling each other out, F net is equal to 0. F net is equal to 0. In general, though, F net, when you have just like general vectors like this, I'm hoping that in the lecture I might have covered this. This is the principle of superposition. Principle of superposition in action. The fact that you can just take all these vectors and you can add them up. You look at, you can simplify the problem by looking at 2 interactions at a time, figuring out what's the force from that, and you just keep on doing that until you get the forces for all of your interactions, okay? That's kind of what we've been doing. And, you know, in this case, I think that segues into part B of this problem. You know, suppose, you know, we had a four-sided polygon, four-corner polygon, and suppose we remove like one of the charges. I mean, what happens, right? What happens? Well, think about it. The moment you remove one of these charges, didn't I like delete this thing from here? Okay. The moment you remove one of these charges out, okay, and that means that your force diagram isn't going to be in equilibrium anymore. One of these vectors is going to have to go. This one actually. So say, you know, remove Q1, your force diagram is going to end up looking like this. Okay, one is gone. And so what ends up happening is that these guys end up canceling out, and now you have a net. F net's going to equal oh my god, what just okay, all right. Dude, I'll like move something here. Okay, just forget about it. So, yeah, so remove this guy. This thing goes. These guys still cancel out, but you have a net F from this interaction here, net force from this interaction. And so, you know, your F net is going to be and the particle is just going to move, you know, in the direction until infinity, pretty much. But that answers that question. Let's see, what about here now? 13 equal charges here, placed at the corner of a 10 to 30-sided polygon. What is the force? Yeah. You know, and I think the rest of this question is just, you know, redundant, right? We made the point. If, you know, the number of vectors, if you get this kind of like vectors going in different directions, cancel each other out, there's pairs of them, then you get equilibrium. The moment you don't have pairs anymore, you get that the net force is, you get a net force. Yeah, so that's problem 2.1. You know, if you want to go off and like work this problem out, like the way Griffiths is saying, you know, this is kind of the intuition you use. Other than that, I mean, I hope that this video carries across the idea that you're looking for. The thing that the problem is trying to make you think about already. What was that? Oh yeah, look at that. That was 20 minutes. I think that's all right. I think that's all right. Okay, well, thank you. Hopefully this helps out. Have a good one.